Hans Eberle is a consulting hardware engineer at Oracle Labs. He holds a PhD in computer science from ETH Zurich and an MBA in sustainable management from the Presidio Graduate School in San Francisco. And his general interests are networking and interconnects. He currently works on application layer offloading on network interface cards. And I believe you're a holder of a few patents as well, right? And so he'll be talking about the weighted differential scheduler. Hans?
Thank you, Christoph. So I'm going to talk about a scheduling method that we call weighted differential scheduler. This is joint work I did with my colleague Lodek Olesinski at Oracle Labs. So the outline for the talk is as follows. I will start with the motivation for this work, and then I will talk about a methodology called digital differential analyzer, which has been heavily used in computer graphics. And I will show how our new scheduling scheme is actually derived from this differential analyzer method. And then I will show some simulation results before I conclude. So the motivation for the work, the problem we are trying to solve is to schedule a shared resource among several requesters. Now, we are looking at weighted scheduling here, so there is a weight associated with each requester that says what share of the resource it should obtain. And I should also introduce an assumption I've been making for this work, which is that scheduling happens in fixed time intervals. So we are, people would say in the networking world, we are forwarding flits, and if you're dealing with a variable size packets, as we usually do, you would chop it up into fixed size chunks or flits. So the goal of this scheduler is to minimize jitter, to minimize the jitter latency, basically meaning outputting packets with equally spaced at equal distances. And the goal of this is, of course, to reduce forwarding latency and also to minimize buffer requirements along the transmission path. Packet forwarding in network switches, in particular for traffic that has some real-time constraints, is just one application that's of most interest to this audience, but the scheduling method actually is more broadly applicable to scheduling resources such as processors or memories or whatever. So let me say a little bit about jitter, since that's sort of the goal of this work, to minimize jitter. So I'm showing here a scheduler that is scheduling packets from two flows. One of the flows has weight 2 and the other flow has weight 3. So what the scheduler is going to do, every 5 slots it will output 2 flits from flow 0 and 3 flits from flow 1. So if we take a simple scheduler such as the weighted round-robin scheme, it would start with one flow, let's say with flow 0, output 2 flits, and then go to the next flow, flow 1, and output 3 flits from that flow. Now the result is bursty traffic. So what our scheme, the weighted differential scheduler, or WDS, is trying to do is to interleave these two flows, the packets from these two flows, so that the packets within a flow are equally spaced. Now, if the weight ratios, if the weights are not multiples of each other, then of course this equal spacing is not possible. And that's where sort of these types of schedulers come into play. Now, there has been extensive work on this topic, including our own work, I have to say. So I'm citing here 2 schedulers, the smoothed round-robin scheduler, SRR, and our own scheduler, low jitter scheduler, LJS. So this is previous work. The smoothed round-robin scheduler, to our knowledge, that's the best it's one of the best schedulers in terms of latency jitter. It outperforms the deficit round-robin scheduler. This scheme was probably published about 10 years ago. A couple of years ago, we published another scheme, the LJS scheduler, which actually improves, has lower jitter in most cases, I should say, than SRR. So what this graph shows here is it shows the jitter ratio when comparing SRR and LJS. So on the y-axis, I showed the jitter ratio for these two algorithms, and on the x-axis, I showed the jitter as a function of a maximum weight, where maximum weight is the sum of the weights of the flows. So for this simulation, we looked at merging two flows. And so, for example, for a maximum weight 10, we looked at all possible weight combinations that add up to 10. For each combination, we calculated the jitter, and then we took the average for all the combinations. So any value greater than 1 in this graph would mean that SRR performs less well than LJS, or that, said another way, that LJS outperforms SRR, which it does. So let me now talk about digital differential analyzers, and in particular about differential analyzers used in computer graphics. These algorithms are used mostly for drawing lines, and probably the most well-known algorithm known is the Bresenham line drawing algorithm, which is used to draw a line between a start and an end point on a raster. So the goal of this algorithm is to avoid drift, to avoid rounding errors. So if a line on a raster would be drawn sort of in a simplistic, naive way, if we just went from raster point to raster point, the line would actually slowly drift away from the actual line. If we just looked at the given raster point, took the slope of the line to draw the next raster point, we would just slowly accumulate error and drift away from the actual line. So that's what Bresenham avoids. The accumulation of error. Another nice property of the Bresenham algorithm is that it uses simple arithmetic. It just uses integer additions and subtractions. So let me first show the pseudocode for Bresenham, and then I'll show how we can derive our scheduling algorithm from this line drawing algorithm. So this code is drawing a line from start point x0, y0 to end point x1, y1. There is a main loop. The code has a main loop where for every iteration the x coordinate is being incremented. So for every iteration the x coordinate is incremented, and then in the inner loop it's being tested whether y has to be incremented too. So every time x is being incremented, we are accumulating an error, which is basically the distance between the current y coordinate and the actual y coordinate on the line. So we are accumulating these errors and then check whether we are more than half a raster point away from the actual line, and if that's the case, we increment y to get the coordinate closer to the line. So that's how we keep these drawn raster points close to the actual line. So that's the essence of Bresenham. So now I'm showing how we can derive a scheduling algorithm from this line drawing algorithm. So we have the Bresenham algorithm that I've just explained on the right side and WDS on the left side. So the only differences that can be seen, the code is mostly similar. The difference is the incremental errors that are being added. So for Bresenham, the delta error, the incremental error was the slope, whereas for WDS, it's the weight ratio. Now I should say in this example, I'm just looking at two flows. For the time being, I'm just looking at two flows. I'll later show how this can be extended to more than two flows. And if we look at the other differences or the increments of the coordinates, so when in Bresenham we increment x, that corresponds in WDS to forwarding a flit from one flow, F0 in this case. And similarly, when y is incremented in Bresenham, this corresponds to forwarding a flit from F1 in WDS. And otherwise, the code is exactly the same. Now, I mentioned that Bresenham can be rewritten so that it only uses integer arithmetic. So the way this is done, we just look at the fractions that are being used in the algorithm, and then use the common denominator, multiply the expressions with their common denominator. So in this case, we have the weight ratio with which has to be multiplied by the common denominator 2W0. That's 2 times the weight of flow 0. It's the comparison in the inner loop, and it's the decrement of the error. And now, of course, so we are left with the code on the right side, excuse me, please, which only uses integer additions and subtractions. The multiplication 2 times the weight, of course, is just a shift. There's no multiplication needed there. Now, I'm going to talk about how we can extend the scheme to more than 2 flows. Now, one method would be to just do what I've shown iteratively. So in this example, I'm just iteratively merging flows. I'm using scheduler S1 to merge flows 0 and 1, and then I use S2 to merge the output of S1 with the next flow F2, and so on. Now, the drawback of this method, of course, is that the scheduling time is proportional to the number of flows. So I will now also explain how more than 2 flows could be merged with a non-iterative method. So in this example, I'm merging 3 flows, F0, F1, F2. And basically, this code just combines the previous code sample that I've shown. It just merges 2 copies of that code. So again, the main loop of this algorithm starts out with forwarding a flit from flow 0, and using the ratio of the flow's weights, so that's W1 over W0 for delta error 1 and W2 over W0 for delta error 2, it is then determined how many packets from the other 2 flows, F1 and F2, have to be forwarded. So again, the basic idea is we forward a flit from flow 0, and then we determine how many packets we have to forward from the other 2 flows, so that the weight ratios are being met. Now, before I show some simulation results, let me explain how we are calculating jitter. So jitter here is calculated as the standard deviation of the interdeparture delays. And I'm briefly explaining here what interdeparture delays are. So I'm showing again a scheduler merging 2 flows and the resulting output stream. So the interdeparture delays are the distances between the packets of a flow. So for flow 0, we are looking at the distance between the first and the second packet, that's 3. And then for determining the next distance, we actually append another sequence. So we then look at the distance between the second packet in the first sequence and the first packet in the next sequence. So that distance is 2. So the distances for F0 are 2 and 3. The standard deviation of that is 0.5. So the jitter expressed as a standard deviation of the interdeparture delays means that the lower the value, the less jitter, the closer we get to equally spaced packets. So the results for two flows look as follows. So I'm using the same graph again that I've shown before for the related work. And so here I'm comparing, I'm looking at three algorithms. I'm looking at our new algorithm, WDS. I'm looking at our previous algorithm, LJS. And I'm looking at SRR. So I'm showing the green graph compares the jitter ratio for SRR and WDS, and the red graph is the jitter ratio for LJS and WDS. So WDS outperforms both algorithms, and as I've said before, LJS outperforms SRR, so therefore WDS is significantly better than SRR. For the values I've shown here, going up to weights of 100, we get something like a factor of 2 improvement over SRR, and about 20% improvement for high values in comparison with LJS, I'm sorry. Now, I talked about non-iterative versions, and I'm comparing here several variations of non-iterative algorithms. I'm looking at 4 different algorithms. The first one, that's algorithm, what I call algorithm 4. That's actually the algorithm I had shown before that merges 3 flows. So let's recall how that works. It increments, it forwards a packet from flow 0 and then determines how many packets from the other flows have to be forwarded to keep the error bound. Now algorithm 5 does sort of the error calculation a little bit with more granularity. Rather than only calculating an error value when a packet from F0 is forwarded, algorithm 5 does this for every packet that is being forwarded from any flow. So, for example, if for example, the error value for flow 1 is incremented not only when a packet from F0 is forwarded, but also when a packet from F2 is being forwarded. So the error calculation is done with a little bit more granularity, with better granularity. The results in terms of do we match the weights is the same. So both algorithms do the right thing. They forward the right number of packets. The only difference is how the errors are being accumulated. Algorithm 7 treats the flows symmetrically. So far, we basically had an asymmetric approach where we always start with flow 0, forward a packet from flow 0, and then see whether we have to forward packets from the other flows. So algorithm 7 visits the flows round robin and doesn't treat flow 0 preferentially. And algorithm 8 is an extension of that scheme in that it actually orders the error values and serves the flow with the largest error value first. Now this is kind of computationally expensive and probably is not doable in most implementations, but we just did it to see how it would perform. So looking at these graphs, we can see that all non-iterative versions perform worse than the iterative versions, with the exception for algorithm 8, the purple graph, which has lower jitter than the iterative version for low weights. In all the other cases, we have larger jitters. And this is something I frankly have to say we don't quite understand we don't really understand all the details. There are some more surprises looking at comparing the results. For example, comparing algorithm 4 and 5, we would expect that 5 would perform better because the error calculation is done with better granularity, but counter to intuition, this is not the case. The best performing algorithm for large values is algorithm 7. That's the blue graph. It basically stays flat after for values for weights around 5. So in summary, I've been trying to show how packet scheduling is actually related to another field, to computer graphics, to how people have been using digital differential analyzers in computer graphics. This new scheme has lower jitter than any other weighted scheduler that we know of. It can be implemented with rather simple logic. It only requires integer additions and subtractions. And as I've mentioned before, we would like to better understand the non-iterative, the behavior of the non-iterative versions, and hopefully when we better understand what's going on, also improve those versions. That concludes my talk. Thanks.
Thanks, Hans.